Okay, so we're gonna still do something about 5.2. I split it in two, I told you, so that because it's kind of a lot of calculations you have noticed by now, and the following thing is even a little bit more. So I'm going to do basically an application of diagonalization, namely powers of a matrix. But before I do that, I want to come back a little bit to this idea of similar matrices. Why? So remember, we say that two A and B square matrices, A and B, are similar. That was a definition. If you could write B as the following way for some invertible of the same, all of the same size, yes, invertible P. Now you might say, why on earth? What does that mean? Why is this a good thing and not something else? Okay, that's why is this called similar. And I'm not going to give you the full explanation here, but I just want to show a couple of things that hopefully convince you that this actually is a very good notion. And that therefore it makes sense to go look for a matrix. In general, of course, this is A and B are arbitrary matrix, but what we really want in diagonalization is where we start with an A, and then the B is very special. It's a diagonal matrix. So let's start first with the diagonal matrices. So a diagonal matrix, and I'm going to give you just an example to tell you what. So let's look at the 2 by 2 diagonal matrix, say 2, 0, 0, 3. Okay, and let's look at it how it operates. Perhaps let me undo this. See what I can. No, sorry. Get a bit better paper for this. Undo this paper. So let's do. Let's see how it operates. So you remember a matrix, we can always think of it as an operation, a linear map on R square. So let's look at the effect of such a thing on a vector. So I'm going to take the vector, let's take, say, this vector here. So this would be the vector, this would be 3, 1. So the vector u is the vector here, I'm going to write it in... well, let me write it as a column because we're going to use the column notation, right? So the vector 3, that's the x-coordinate y. Okay. So what is the image of this vector under A? So this is my A here. So we calculate A u bar. Well, let's do the matrix multiplication. And what we get is 2 times 3, that's 6 plus 0. And then 0 times 3 plus 3. I get 6, 3. So let's graph that. So let's make this the green vector. So this is my V down. That's the image of A. So that is the vector 6, 3. Okay. So that is this vector. Now immediately you say, I don't know. Okay, what has happened? Now let's break down. Remember, we can always project vectors orthogonally. And in particular, when we have the standard basis, we can project on the standard basis vectors and we get to regular coordinates. So let's look at the coordinates of the purple one. So I'm going to make them dark purple. Okay, so this is the x coordinate if you want, and this is the y coordinate, right? Or the E1 and E2. Okay. Now what we see about, let's do the same for the dark green, the light, now I have to do light green here. So this is the vector, the projection onto the x-coordinate of the image, and this is... Now what can we say about those? No, look at this one. There's a relationship between, let's look at the bottom one. There's a relationship between the purple, the dark purple one and the light green one, namely, it's twice as long than the new one. Twice as long. What happens in here? It is 3 times as long, and the vertical one. The vertical one here has size 1, now it has size 3, so 3 times. So that's what an eigenvector does. It stretches out in a certain direction. So in other words, it kind of says that if you have a diagonal matrix, it operates like a stretching in one direction and a different stretching in another direction. Okay? You can think of it as how forces would work. A force works on, if you know a bit of physics, vectors represent forces and the projections represent the movement in that direction. So in the x direction, you're going twice as fast, and in the y direction going 3 times as fast. That's what the diagonal matrix says. Now, what is then this say? If I now take an invertible P and apply it to A, what changes? Well, I'm not going to explain this, but because it's not part of the course here, but what it does is basically saying, okay, you change the vectors, you change the basis. Remember, so our basis system that we had here, I'll do that in brown, was, if you want, E1 and E2, the two basis vectors, right? And if you take an invertible matrix and look at an invertible matrix corresponds to a change of basis, and this then becomes the new matrix in that new basis. So, what does it now all mean? So if we start with, so this, okay, I call this A, perhaps I should call this D here because it was a diagonal matrix, right? If you start with an arbitrary A and you diagonalize it, then the diagonal matrix, we know how it acts. It acts like multiplication with the first eigenvector in one direction, with the second eigenvector in the second direction, and of course, in higher dimensions there are more directions, but it's exactly the same. That's how the diagonal matrix works. Now we said that a change of a formula like P minus 1 AP just means that the original A does the same thing, but not in the standard basis, but in a basis that is the change of basis that you get through this matrix P. I'm a little bit vague how this works, but you have to trust me. That means that there was a basis such that according to that basis, if you would project onto the one basis vector, your A acts as if it multiplies it with 2, the first one, and on the other one it multiplies the coordinate with 3. So that is why we look at similar matrices. So let me rephrase this a little bit. If you have two matrices that are similar, that means they are the same transformation viewed in different bases. Okay? And in particular, if you diagonalize a matrix, then you see that the action of that matrix becomes a diagonal action in a particular system of coordinates. And that is why we do this. Okay, that's the first thing I want to say. But I want to also point out a couple of algebraic facts. I'm going to get rid of this checkered pattern. I don't know, it kind of disrupts me. Okay, so another thing, so let's look at it again. So we have B. B is now still, I'm doing rather general things, right? And then I'll get back, oh, no, not the previous one. Let's calculate the determinants. Well, go look up what happens, how do you calculate the determinant of a product? Well, luckily that is just the product of the determinants. Okay, it's not true for sums, but it is true for products. So determinant P1, determinant A, determinant P. Okay. Now, we know that P is a non-zero element because P is invertible. So we know that the determinant of P is non-zero, but we don't know what it is. Okay. What about the determinant of P inverse? Again, go look up in the topic on determinants. We actually showed then that it actually is the reciprocal of the determinant of the original P. So it's kind of, that's inverse, you kind of expect that it's going to be the reciprocal, right? It's multiplicative here. Okay, so this means what? This first quantity is just 1 over the determinant of P, and then top we have determinant of A times the determinant of P. Now you might say, can I do this? Can I write something in the denominator? Not matrices, but these are numbers, right? These are real numbers. These are real numbers. So I can write a non-zero real number. So I can do the usual things with real numbers. So in particular, I can cancel. So what is the result is that this is just the determinant of A. So similar matrices have the same determinant. So that's interesting, right? You don't lose at all the determinant. And it's not surprising if what I was saying was true is about this change of basis vector. The determinant, you can also interpret the determinant in a particular way. I'm not going to entirely explain this, but just briefly, what the determinant does if you have a linear matrix, it matches it. If you take now a parallelogram, or actually any object, any like let's say a circle. They take a circle and look at the image of all the points on the circle. Then the image might not be a circle anymore, but what it does is the area of the new object is going to be the area of the previous object times the determinant. So the determinant is kind of a global scaling factor. Okay, that's definitely not part of this course. That is a higher geometry course, but this tells me again, if I do similar matrices, well, the effect is the same. It's supposed to be, right? Because they were just same operation, just in different coordinates. But it's not the only thing that stays the same. Let's look at an eigenvector. So let U be an eigenvector of A with eigenvalue, let's call it just lambda. Okay, but now lambda is not a variable, lambda is a number. You don't like it? Okay, let's write eigenvalue C, where C is now a natural, a real number. Okay, so what does this mean? That means that A times U is C times U, right? That's what it means to be an eigenvector. And of course, it also means that this is non-zero. Okay, that's the definition of an eigenvector. Go look it up. Now let's look at the following vector. The vector V that I get by P inverse U. Okay, I think I got it right here. Yeah, okay. So P, the inverse of P, they're all square matrices of this. I didn't say what the size is. It could be 2 by 2, could be 3 by 3, could be even higher. And so the result of P minus 1 is a vector, is a matrix, and I can do this. I can calculate this vector, right? So I now want to compare this. What is this vector do? How does B act on this vector? So let's look at B V bar. Okay. Now I'm going to replace B by this formula. So I will do this. So this becomes P minus 1 A P, and I'm going to replace V by this guy. So that's P minus 1 U. What you notice is that when you have a matrix next to its inverse, then they cancel out, right? So what we get? Okay, so this simplifies. Is that clear? That this is the identity matrix now. So we say we are size n. Yeah. In other words, we don't have to write it. Right? It's an identity matrix. So the result is basically, well, we have P inverse stays there, A stays, but these two kind of cancel out, and we have U left. Okay. AU, wait, I have this formula for AU, so let's do this in blue now. I'm substituting this one, so I get P minus 1, and now AU, I replace this by my C times U. Now C is a scalar, and where the multiplication of matrices, the order is very important. Scalars are just scalars, they can move around, so we can move the scalar outside here. So let's do that. So I get C times P minus 1 U bar. I'll just move it out. But wait a sec. I know what this is. Look at I have this is the green guy here. That is just V. So this is C times V. Oh, look. What is this? This equation tells me that V is an eigenvector of B. Well, okay, it's a different vector than original U, but the eigenvalue is the same. So you see that if you have a similar matrix, they have the same eigenvalues. Now, not surprising, because if we do a diagonalize, what we do? The diagonal matrix becomes a matrix with the eigenvalues on it. And what are the eigenvalues of a diagonal matrix? The diagonal elements, right? And those were the eigenvalues of the original one. So it's something we knew, but here we see it on paper, if you want. Okay, that's all I want to say about general stuff, but then I want to come to the application. So what happens, well, I still want to stay a little bit more, I said sorry, I want one more thing I have to do before I can do this. Let's calculate b square. Okay, now b was p minus 1ab. So b squared, of course, just means b times b. Be careful. It doesn't mean that you have to square the elements. Some of you might, I've seen it done, people do this, but that's not what it is, right? It is just multiplying b with itself. That's, well, something you have to carry out. Now, b, remember, was, here it is, p minus 1ab, p, right? p minus 1ab. That's the first b, and the second p is also that, p minus 1ab. I'm not writing the dots in the middle anymore, it's all multiplication. Ah, we see again, this pair here, they cancel out, right? So we can, again, a cancellation. So we get p minus 1, a times a, well, that's just a square, p. So what does it say? So remember, b was p minus 1ab. So b was similar to a via this matrix p. And then we see that b squared is similar to a squared via the same matrix. So not only are the powers, if two matrices are similar, their powers are similar, but they are similar using the same matrix p. That's kind of neat, right? And that's the thing that we're going to exploit. Now, I have to stress each time that this p, when you write down a similar relation like this, the p is not unique. And we have seen this when we do this with diagonalization. The p is never unique because you can, for one thing, decide what the order of the eigenvalues are. And then even within eigenspace, you can take whatever basis you want, in whichever order. Okay, so let's now use this. So how am I going to use this? Now, so imagine that that b, now, this is the general case, but now suppose that B is actually a diagonal matrix, D. Okay, let's take an example now. Let's take n is 3. So suppose it's 0, 0, 0, 1. So that's an example, right? I haven't said what A is, I'm just saying suppose A is so that we get this D. So now, what is B square? So D square, B square is now D square, what is that? So what is the square of diagonal matrix? Now carry this out and you see, we have discussed this, that it actually is really now what we sometimes do wrongly, but now it's correct, square the elements, the diagonal elements, 9, 9, 1. So now we are right by just squaring everything. For an arbitrary matrix this is incorrect, but for a diagonal matrix is correct. So in other words, to calculate the square of a matrix is quite simple, okay, of a diagonal matrix, or even a higher power. I did this for a square, but now think about it. What happens with b cubed? If I do b cubed, I'm going to let you do it yourself, you'll see that each time we have a p and a p minus 1 next to each other, so they all cancel out, and you get, so what we'll get is, so check for yourself, so see that you understand this, that this is what you get, 2. Okay, so work it out. I'm not going to show you. It's very simple. It's just the same calculation as before. And so with any other powers. And again, what's the cube of a matrix? In this case, it would be just cube everything. 27, 0, 0, 0, 27, 0. And of course, a cube of 1 is just 1. Okay? So this is what we're going to exploit. Okay, so let me now go to an example. Let's start with an example. So we have a matrix here. Where was my matrix? Sorry. I have to take, this was number 5. Yeah, okay. So let's take A, the matrix 1, 0, 6, negative 1. And I want to calculate A cube. Now, of course, in this case, it's kind of ridiculous. I could just work it out. That times that times that. Okay, so if you want to be challenged, let's do a to the power 10. That gets a little bit more challenging, right? Now I don't want to do the big numbers, so I'm going to go back to my 3 here. But I just want to show you, although in this particular 2x2 matrix case, it's kind of silly to do this very complicated thing that I'm going to do. In general, it's actually really, really interesting. A very good way of finding powers of a matrix. And I should repeat that in many applications, powers of matrices are very important. So it is an important technique to be able to do this. At this point, I cannot show you why, but just have to trust me. For now, you just think of it as a little challenge. So how does it work? So step one. So, okay, a cube using diagonalization and not just multiplying. So on a quiz, when I ask this, the next quiz will be about this. You have to do it this way and not just multiply the matrix with itself. Okay, that will not give you any credit. So, step one. Well, the first thing we're going to do is diagonalize this matrix. And so, if we want to diagonalize this matrix, we're going to do the characteristic equation. And that is subtract lambda from the diagonal. Well, we put this equal to 0, and this is very simple. That is 1 minus lambda times minus 1 minus lambda. If we put this equal to 0, this is lambda equals 1, and this is lambda equals negative 1. Be careful all the negative signs here, right? Because, I mean, if this is lambda minus, this is minus lambda plus 1, right? Okay. Okay, so we have two eigenvalues. So we know already that the matrix is diagonalizable, right? Because they're all different. If you have all different eigenvalues, then you're good, for sure, because you have one vector for each, and that's going to give you the P. So step 2, the eigenspace for lambda equals, let's start with lambda equals 1. So we subtract 1 from the diagonal, and we get the matrix 0, 0, 6, minus 2. We have to row reduce this. Okay, we have, I mentioned this, right? You cannot not always expect. Well, first of all, we should swap the two rows, and yeah, okay, let's do this. Let's take our time. It's really very quickly, and then we sometimes have to have fractions. You cannot expect this to be not happening. So we have R1 divided by 1/3 of R 1/6 of R1, and so we get finally 1 minus 1. What am I doing? Yeah, minus 1/3, right? Okay. And then 0, 0. Okay, so we have our pivot variable, and we have to have a free variable always, otherwise something is wrong. So we get x1, x2. And this equation tells me that x1 is 1/3 of x2, and x2 is just itself. So we get x2, 1/3, 1. So this is a basis vector, but we have a choice. And since we don't like fractions, we can take a multiple. We can x2, we can take x2 what we want here. So I'm going to take x2 equals 3 to get rid of the, I don't need to, and you can do it without it, but I just don't like fractions. So my basis vector is going to be 3 times this one, so this is 1, 3. Okay. Because I'm going to have to put this in a matrix P, I'm going to have to find the inverse of this P, so it's better to not have too difficult numbers here. Okay, that's what the eigenvalue for lambda is 1. What about eigenspace for lambda is -1. So now I have to subtract -1 from the diagonal. So yeah, my A keeps disappearing here. So this is the matrix. I'm going to try to do it here. Subtract 1 from the diagonal. So I get a 2, 0, 6, minus 0. Okay. Okay. So this is even quicker to do. I can do row 1 divided by 2 and row 2 divided by 6. Okay. I get 1, 0, 1, 0, and then of course row 2 subtract row 1 from that, and I get the matrix 1, 0, and 0, 0. So we have our pivot is x1, and the free variable is x2. Well, I didn't know why I shouldn't have circled the 0 here. Doesn't make sense. Okay. Okay. So we have x1, x2. From this equation, we see that x1 is just 0. And x2 is of course just itself, so we get x2 times 0, 1. So this is our other basis. Good, we have, I'm going to do this here. So step 3, we can write down what P and D are. I did 1 first and then -1, so let's keep the order that I did it in. You don't have to, but I'm already confusing myself all the time, so I try to. So we have this basis vector 1, 3, and we have this basis vector 0, 1. So this is P. Great. So let's find P inverse. Step 4. You see why we need P inverse. We need it. It's not just a fancy thing that I'm asking you, but here, P inverse. Okay. Yeah, so how do you do this? We start with the original P, 1, 0, 3, 1. Oh, no, P inverse, what I'm doing. You can do it this way, of course, but sorry, I was thinking about something else. Come on, how do you do the P inverse? How do you do the inverse of a 2 by 2 matrix? We know what to do. Well, first of all, we need a determinant. What's the determinant of P? Well, that's easy, that's 1, right? From the determinant formula. And then the inverse of P is 1 over the determinant. And then what we have to do is, well, 1 over 1 then. Yeah, so let me just write 1 over 1, right? So 1 over 1, meaning the determinant. And what we do is we switch the diagonal elements, big deal, and then we put a minus and the off diagonals. If you go back to look at this formula. So this is my P, and 1 over 1 is kind of distracting me, so I'm going to get rid of it. So that's the inverse. That's just using the formula for the inverse of a 2 by 2. But you could do in general, you have to do the method of a row reduction. Okay. So that's was step 4. Now we wanted to calculate a to the power 10, right? Where was my question? I said a to the power 10. Let's do a to the power 10. Why not? Okay, because I can even do here a to the power 20. If I really want to discourage you to really multiply a times a times a times a, blah, 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 you'll see how easy it is. So step 5. So what we have, let's write down what we have. So at this point, we have that the diagonal matrix is P minus 1 A P. Okay. What we want is a to the power 10. So I'm going to solve this equation for A. Now we have to be careful with these matrices. We cannot just multiply with the inverse. We have to multiply on the right side of it. So the first thing I'm going to do is multiply by P on both sides here. And then I'm going to multiply, I'll do it in a different color, with P inverse on this side. Why do I do this? Obviously now, I hope you see why I'm doing this, because of course these two guys cancel out, these two guys cancel out. So what I have is P, D, P inverse is just A. So what is A to the power 10? A to the power 10 is the 10th power of this matrix, but we have already noticed that, look here where I wrote this up here, where was this? Here, right? We saw that if you have a matrix that is similar to another matrix, then the square of the matrix is similar to the original matrix with the same p's. So this is what happens here too. So we can work this out, but this actually really is now the same thing. P, d to the power 10, p minus 1. The same p here. Why is this easier? This is the crucial step. D to the power 10 is something I can write down easily because it's a diagonal matrix. And that means just take the power of each of the diagonal elements. That's why I cannot do this in general, but with diagonal matrix I can do that. And the diagonal matrix is 1, 0, 0, negative 1. And it's even easier here, really the numbers are very small. 1 to the power 10, that's just 1. Minus 1 to the power 10 is also just 1. So I just get the identity matrix here. Okay? So I get the identity matrix here. So, but then I have P times P inverse. This is just identity matrix. This is just identity matrix. Funny, right? This is something you might not think. In fact, in this case, actually, if you calculate a square, you already see that you get the identity matrix. But I just want to show you, this is how we're going to do this quickly. Now, this might be not convinced. This might probably not convince you to say, okay, you did this now, but what's the big deal here? So I'm going to do a matrix a little bit of bigger size here. I do a 3 by 3 matrix. Okay, I'll take the one that they also do in the book. So let's do this same example here for this matrix here. So now a 3 by 3, and the matrix I'm going to work with is the matrix 0, 0, negative 2, 1, 2, 1, 1, 0, 3, and I'm going to ask you what is a to the power 5. Okay? And you could still do this, a times a times a times a, and I guarantee you, if you do this just by hand, you're going to make mistakes, because it's too many numbers and they get bigger and bigger, and okay, so let's do this, the method, so via the method diagonalization. Again, I'm not writing it down. So, characteristic equation. We did actually already discuss this matrix, so it's hopefully some of the things are familiar here. We subtract 2 from the lambda from the diagonal. Okay. Then I'm gonna, I have this nice column here, so column 2. So they get 2 minus lambda, and then what is left is minus lambda minus 2, 1, 3 minus lambda. So this is equal to 2 minus lambda. I should put it in between parentheses. And then is minus lambda, 3 minus lambda, minus minus plus 2. So this is minus 3 lambda plus lambda square plus 2. So, and how this is factored? 2 minus lambda. I need two numbers that, well, let me know, I don't know what is plus or minus. Two numbers that multiply to 2 and add up to negative 3. Negative 2 and lambda negative 1, right? Yep. Okay, so this is equal to 0. We see this gives lambda is 2 twice again, and this is lambda is 1. Okay, so that's the eigenvalues, eigenspaces. This, we are not guaranteed that this is a diagonal matrix. And so this method only works for diagonal matrices, by the way, right? If the matrix cannot be diagonalized, you cannot do this. So let's hope that the eigenspace for lambda is 2 has dimension 2. Because that's the only one that can cause problems, right? We might have too little basis vectors here. Okay, so the eigenspace for lambda is 2. That means we're gonna, in this matrix, replace lambda is 2. And we get minus 2, 0, minus 2. 1, 0, 1, 1, 0, 1. And it's rather quick to do this. We first divide row 1 by minus a half, and then you see you get 3 times the same thing, so that 1, 0, 1, 1, 1, 0, 1, 1, 0, 1. So row 2 minus row 1, and the same with row 3. I get 1, 0, 1, and the rest are zeros. Okay, so we have our pivot, x1, and we have 2 free variables, x2 and x3, so we get x1, x2, x3. x1 from this equation is equal to negative x2, and x2 and x3 are equal to themselves. So we get x2, 0, 1, 0, plus x3, minus 1, 0, 1. These are the two basic vectors, no need to clear denominators here. Okay, so that's the one for eigenspace for lambda is 2. We have the right amount, because we know that lambda equals, what was the other one? 1 is not going to cause any problems. It's going to give us just 1, that's what we need. So we have to put in this guy, lambda equals to 1, we get minus 1, 0, negative 2, 1, 1, 1, and 1, 0, 2. Okay. Again, I'm going to do row 1 minus row 1 to get rid of the negative signs. I'm going to cheat a little bit and do it on the fly here. So this is gone. Yeah, okay. It's a movie, right? You see what I've done. Okay. So now I can use this pivot here to row 2 minus row 1, and row 3 minus row 1. I'm gonna get, so I'm gonna do times minus 1 added up there, so you get 0, 1, minus 1, and that is just 0, 0. oh, sorry, I forgot to copy the top one. That was the first row, this is the second row, and this is the third row. Okay. Yeah, good. This is the row reduced form, so I can stop. This is my two pivots, x1 and x2. We know that there should be only one free variable. Again, if we would have two free variables, that would be another problem, because then we have too many. That's not possible, right? So, okay. Well, it's possible, but that means you made a mistake. So we get x1, x2, x3. x3 is just itself. And what is x1? Well, from this we see that it's negative 2 times x3, and from this equation we see that x2 is equal to x3. So we get x3 is negative 2, 1, 1. Okay, so step 3, we know what p is. Or we can determine what p is, and at the meantime we do d. We put the eigenvalue 2 first and then 1, so I'm going to keep that order. And then here comes these two basic vectors, 0, 1, 0, and minus 1, 0, 1. I can do a different order. Let me do a different order, perhaps, just to show you that I can do this. Because I think previous time we solved the same question, and with the given order, the order that's just first did. So I'm going to do a different order. And then this one here. Of course, I mean, since I put the 2's here, I have to put the two basis vectors there, right? You even are allowed, by the way, to put 2, 1, 2, but then you have to make sure that the first and last column correspond to the eigenvectors 2 and the middle one to the eigenvector 1. You could even do that. I wouldn't recommend it because you get confused yourself, but okay. So step 4 is we noticed we need P inverse. And here it's a little bit more work, not that much. So we take our matrix and we augment it with the identity matrix. Then we start row reducing. Okay, we have our pivot. Oh no, well, we need to do row 1 minus row 1. This one I have to be careful, right? Because there's more than just the original row. So we have to make sure that we don't do anything wrong here, that the effect of our row operations also are reflected on what we do there. Sometimes you forget about that. I mean, I do. I'm like that. You know me, tête en l'air. Okay, so here 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1. Okay. We have our pivot, and so we're going to do row 3 minus row 1. 1, 0, 2, negative 1, 0, 0, 0, 1, 1, 0, 1, 0. So negative 1, so that's a 0. We have 0. Negative 2 plus 1 is negative 1. Negative 1 times negative 1 is 1. That's just a 0, and that's just a 1. Great. Oh, we're almost done. We have to change the sign of the third row. Let's write it out. I don't want to make any mistakes. 1, 0, 2, minus 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, minus 1, 0, minus 1. Okay. This is the pivot that is not in row reduced form yet, reduced echelon form, so we need to do two more row operations. Row 1 minus 2 times row 3 to get rid of this 2, and row 2 minus row 3 to get rid of this 2, all using this bottom pivot here, right? That's why we used row 3. Okay, what do we get? So we do this negative 2 times added there, so we get 1, 0, 0. Negative 2, that's positive 2, minus 1, that is 1, that nothing happens, and here we do positive 2. Okay, so then we have 0, 1, so now we do negative 1 add up, 0, negative 1, that's a 1, we have a 1 there, and that is also a 1, and then finally 0, 0, 1, minus 1, 0, negative 1. So this now is P inverse. Now I don't trust myself, so I'm going to check. It's not necessary, but just to make sure that I don't make mistakes. 1, 0, 2, 1, 1, 1, minus 1, 0, negative 1. So how do I check? Well, what I'm going to do is multiply them and see whether I get what I need to get, namely the identity matrix. Minus 1, 0, negative 2, minus 1, 0, negative 2, 0, 1, 1, 0, 1, 1, and 1, 0, 1. The numbers look very similar, right? But that doesn't mean anything. That's just because they're still rather simple matrices, that's why. Okay. Sorry, double checking here. No, I think I made a mistake already. Before I go on, let me double check here. What? No. I'm right, but let's just double check it. Okay, so we're gonna, and this element is minus 1 times 1, minus 1 plus 0 plus 2, that is 1, right? Yeah. And 0 plus 0 plus 0, great. Minus 2 plus 0 plus 2, yay. Then the second row, minus 1 plus 0 plus 1, 0. 0 plus 1 plus 0, 1. Minus 2 plus 1 plus 1, that's 0. Minus 1 is 1 plus 0 plus minus 1, yep. 0, 0, 0. And then finally, 2 plus 0 minus 1 is 1. Okay, it worked. So it was correct. But so I'm putting this between parentheses saying this is not part of what you need to do. Now, where are we? So let's write down what we have. So we have that our diagonal matrix is P minus 1 A P, and we know that from there we can, this is the same operation that we did here. Where did I do this? Right here. We get the same similarity relation, but with the role of P and P inverse reversed. So we get P times D times P minus 1 is A. Now what is the question? The question was A to the power 5, I think, right? A to the power 5. Okay, so what is A to the power 5? Well, we know that this is P times D to the power 5 P minus 1. Again, if you don't remember anymore why this is, just work this out. Just work out what this means. Say, I just want to show you what A squared is again. P D P minus 1 P D P minus 1, right? I write A twice. And then the P and the P minus 1 cancel out, so we get P D squared P minus 1. That's the magic that happens, and it happens with higher powers as well. Okay? That was how it worked. Okay, so we just have this. We can now write down everything here. We know what P is. Be careful, this is P now, not P inverse, right? Okay, so this is P, which was, this was my P here, right? This was P, this is my P inverse. That's why I brought them here, that I have them. So that is minus 1, 0, negative 2, 0, 1, 1, 1, 0, 1. Okay. Now what is D to the power 5? What was D? D was this guy. So let me write D here. I will do it on this side. We don't need this anymore. So D was 2, 0, 0, 0, 2, 0, 0, 0, 1. And then D to the 5th is just take the 5th power of the diagonal elements. 2 to the 5th is 32. And that is just 1. Okay. So this is 32, 0, 0, 0, 32, 0, 0, 0, 1. And then multiply with the P. Sorry, I need some space. I'm going to get rid of this again. And then we get P inverse, P inverse, P inverse. Be careful that you write the correct things here, right? So the formula is upside down here because we solved here for A, right? And so P inverse is the matrix, this guy here. It's 1, 0, 2, 1, 1, 1, minus 1, 0, negative 1. Okay, so let's work this out. I'll start from the back. It doesn't make matter from which direction I do it. Okay, so 32 plus 0, that's just 32. This element is 0 plus 0 plus 0. This element is 64 plus 0 plus 0. Sorry. Okay, then 0, times 32 plus 0, so it's 32. 0 times 32, that's 32. 0 times 32, that's 32. The last one is 0 times 0 is negative 1. 0, negative 1. Okay. See, in this, perhaps this way is, if you do on the back, it's kind of easier to do if you see what actually happens, but don't try to guess anything, just do all the calculations here. Okay, so, but we have to still multiply this now. Okay, that's our first element here. Minus 32 plus 0 plus 2, right? So that is minus 30. 0 plus 0 plus 0. Then negative 64 plus 2, so minus 62. Alright, the second row, 0 plus 32 minus 1. 0 plus 32 plus 0. 0 plus 32 minus 1. And now the last row, 32 plus 0 minus 1. 0 times 0 times plus 0. And then 64 plus 0 minus 1 is 63. Cool, huh? So that's how you can take very quickly the 5th power, and I could even do higher powers here. In the book, actually, they work out to 10th power. The numbers get bigger, but you see, actually, the calculations are not so bad, because these are very small numbers. Now, imagine if you would calculate this matrix. Okay, so suppose you have to calculate a to the power 6th. Now, this was a to the power 5th, so you have to multiply this with a. You see, now you're getting a lot of big numbers, and it gets a lot of additions and so, and the chance to make an error is much bigger now. Alright, so this is the application. That is part 2 of this topic, and I'm going to assign some homework problems, and then we do a quiz next time. Okie dokie? Alright.